We will now walk through an example or a whole process of generating as many counterintuitive examples as we like based on Sun's impossibility result. So Sun proposed another list of 4 axioms. We've seen the first 2. Each input list complete and transitive. The output list complete and transitive. We've seen Pareto. If every input list prefers A over B, then the output should also say A is better than B. The fourth one is again the problematic one. It says there should be at least 2 decisive voters. What is one decisive voter? It says that a decisive voter is one where they have the voter has at least one pair comparison where she holds the absolute power. Okay? If she thinks A is better than B, then even if everyone else thinks B is better than A, the output should say A better than B. Now, of course, that's a very strong power, and if there's only one such person with these powers, then that is a dictator. So there needs to be at least 2 decisive voters for the system to be a real voting system. But still, that gives 2 or more voters a very strong power to rule over the others. And it turns out that this strong power would make voting systems impossible. There is no voting system that can satisfy all 4 axioms. It's impossibility result again. And what happens is that the decisive voter imposes a strong externality on all the other voters. And therefore this blocks axiom 2. Just like IIA in Arrow's system blocks axiom 2 and possibly leading to cyclic output even though all inputs are transitive. And we'll illustrate this through a way to generate as many examples as you want. And here is how those examples can be generated. Let's say we got 3 voters and 5 candidates. Okay, voters 1, 2, 3, candidates A, B, C, D, E. Let's look at these pairwise comparison, A, B, B, C, C, D, D, E, and E, A. To start constructing counterexamples, we can just say that each of the 3 voters have the identical and cyclic input, which is A better than B, better than C, better than D, better than E, which is in turn better than A. This clearly is a cyclic input, and therefore should not be allowed. But we're not done yet. This is intermediate step. And 2, 3 have the same. Now, let's say voter A is the decisive voter on the AB pairwise comparison. Voter 2 is the decisive voter on the CD pairwise. And voter 3 is the decisive voter on the EA pairwise comparison. We denote that fact by these 3 red phrases. And now we want to say is that we would like to make these 3 input lists transitive. Okay, not cyclic anymore, and yet the output will be cyclic. Okay, clearly right now the output is cyclic. So we want output to be cyclic and yet input not to be cyclic, because our goal is to generate counterintuitive examples. And indeed we can do that. We just simply need to look at the pairwise comparison where voter 1 has the decisive power, and then swap the AB for voters 2 and 3. Okay, similarly, where voter 2 has decisive power, swap CD for voters 1 and 3, and where voter 3 has decisive power, swap that pairwise comparison for voters 1 and 2. Because now if you look at each of the 3 voters' input list, it is transitive. Okay, this says, for example, the first one, A better than B, B better than C, D also better than C, D is better than E, and A is better than E. That is not cyclic. That satisfies all the transitivity that you need. Similarly for the other 2 voters, 2 and 3. And therefore now the 3 inputs are indeed transitive. And yet, because we only flipped where there is a decisive voter, so the output remains transitive. Still A better than B, B better than C, C better than D, because voter 2's vote is the decisive vote, D better than E, and E better than A, because voter 3's vote is decisive vote. We just flipped the non-decisive voters so that all inputs are transitive, and yet output is still transitive, is cyclic, because A better than B, then C, then D, then E, in turn, then A. That is a cycle from A back to E. Now we got more than one decisive voters. We follow the Pareto principle. All inputs are cyclic and yet are transitive, and yet output is cyclic. In fact, if you remember all the way back to lecture 1, when we talked about prisoner's dilemma, when we introduced a game to model competition, that is a special case of sans counterintuitive examples too, because we can view that game in the following light. The two prisoners, again, 1 and 2. Okay, numerical values doesn't matter in this illustration. They each got 2 choices: not confess, confess, not confess, confess. Okay. Prisoner 1 can be the decisive voter between confess or not confess, between the 2 columns. Okay? And prisoner 1 would say, you know what, I think confess is better than not confess in any case. So it says B is better than A, and D is better than C. Similarly, prisoner 2 would say that confess is better than no confess, so C is better than A, and D is better than B. So out of the 4 possible candidates, A, B, C, D, describing the 2x2 configuration of this game, one prisoner says B better than A, D better than C. The other prisoner says C better than A, D better than B. Since they control these actions, they are the decisive voters for those 2 pairwise comparisons respectively. And both agree that A is better than D. Okay? If both decide not to confess, that's better than both confess. And now here comes the problem. The dilemma is now reflected in this cyclic output of the 4 candidates voting result. Because A is better than D, both agree. And prisoner 2 says D is better than B. And prisoner 1 says B is better than A. And they are the 2 decisive voters for these 2. And therefore you form a cycle. A better than D, better than B, better than A. Similarly, you have another cycle the other way around. A better than D, better than C, better than A. And that is why you see prisoner's dilemma. Because the 2 prisoners is each a decisive voter between 2 actions. And together with a common sense choice, that leads to 2 cycles. And there's therefore no transitive result that satisfies both prisoners' needs. So now we have come to the end of this lecture. This is a relatively short lecture, but we're going to have 2 long lectures coming up in the next 2 lectures 7 and 8. The key message here is that Wikipedia's success depends on the positive network effect as well as good faith collaboration. The forming consensus of collaboration can be modeled by either bargaining or voting. We spent a little bit of time on bargaining. And for voting, we saw that it may not satisfy some intuitive conditions as it compresses many rank order lists into a single one, such as IIA, which is the flawed intuition. And it's an important principle that a voting can indeed be made sensible, and as it's a universal right to provide the bridge between individuals and the aggregate, an effective means to provide check and balances against absolute power, and forms the foundation of the consent from the government to the government. So this is an important principle that we got just a little bit of time to cover, and we will move on now to influence power models in the next lecture.